In the depths of space, something unimaginable is happening, something that could change our view of the universe. In the silent darkness of the cosmos, in its most remote corners, the James Webb Telescope has captured a strange and unsettling phenomenon. This event has left scientists frozen in anticipation, pondering what exactly they have discovered. A newly born entity known as the protostar L1527 has appeared in these mysterious images. What does this mean for us? What secret does it conceal? Its emergence may unlock new insights into the beginnings and endings of star systems, and perhaps into something far more profound and disquieting. Hidden processes, now visible through incredible technology, compel us to reassess everything we thought we knew about space. But what mysteries lie behind these images? What forces are concealed within the birth of a new star? The future of science, and perhaps our understanding of existence itself, now hinges on unraveling this new cosmic enigma. The James Webb Space Telescope, named after the renowned astronomer and science popularizer, represents a cutting-edge and powerful tool in astronomers' arsenal. Its development began in 1996. It was designed to study the cosmos with unprecedented precision and sensitivity, crucial for early-stage star formation astronomy. The James Webb Space Telescope, JWST, builds upon the legacy of the famous Hubble Space Telescope. However, unlike Hubble, which focused on observations in the visible and ultraviolet wavelengths, James Webb specializes in infrared radiation. This capability allows it to penetrate dusty and gaseous clouds that often obscure visibility in other ranges and peer into the farthest corners of the universe. One of JWST's key objectives is to study the early stages of star formation. Stars are born from gas and dust in molecular clouds, which begin to collapse under their own gravitational pull. This process is complex and lengthy, and our existing instruments have not previously been able to provide such detailed data on the initial stages of star formation. James Webb is equipped with high-resolution instruments that enable astronomers to observe details of processes happening billions of light-years away. This includes the ability to discern individual star-forming regions within galaxies and study the chemical composition of the clouds from which stars emerge. The high sensitivity of James Webb allows it to detect even the faintest signals of infrared radiation from the most distant sources, opening new possibilities for studying exoplanets and investigating atmospheric phenomena around distant stars. Thanks to these capabilities, scientists can more extensively study protostars, which are unique astronomical objects in their early developmental stages. The age of a protostar is a key indicator of its evolutionary state and determines how it will evolve in the future. What are the specific features of protostars that make them so unique? Among known stars, a protostar can be considered one of the youngest, existing for only about 100,000 years. This relatively short period on cosmic scales makes it a subject of special interest for astronomers and researchers. The process of forming a protostar begins with the gravitational collapse of gas and dust in interstellar space. Under the influence of gravity, the mass of material begins to compress and heat up, eventually triggering nuclear reactions in its core. This process is a pivotal moment in the star's formation, initiating energy release and luminosity. Studying young protostars deepens our understanding of star formation and the dynamics of young stellar systems. The youth of a protostar is linked not only to its age, but also to the unique conditions in the surrounding interstellar gas and dust, which continue to influence its environment and evolution. Astronomers employ various research methods, including observations across different ranges of the electromagnetic spectrum, from infrared to radio frequencies. These observations help identify signs of young stars and their surrounding environments, including accretion disks and molecular clouds from which the star is forming. Star L1527 is an intriguing object of study in the context of star formation and protoplanetary disk evolution. Positioned within the throat of a protoplanetary disk, it resides in a zone where conditions for star formation and growth are particularly favorable. Protoplanetary disks are ring-like structures composed of dust, gas, and remnants of matter that form around young stars. These disks facilitate material accretion onto the star and the formation of planets and other celestial bodies. The throat of a protoplanetary disk is a crucial region because here the material density and pressure are sufficiently high to initiate gravitational collapse of gas and dust clouds, leading to the formation and growth of stars. The material density in this region can reach about 106 particles per cubic centimeter, with pressures on the order of 10 to 9 bar. This process begins with a molecular cloud that starts collapsing under its own gravity, forming a protostar. A protoplanetary disk then forms around the protostar, composed of matter remnants that did not accrete into the star during its formation. Star L1527 resides within such a protoplanetary disk, making its observation particularly interesting to astronomers and scientists. Why does studying this star generate so much interest among researchers? Studying this star helps us understand the formation and development of stellar systems in the early stages of their evolution. Observations of L1527 illustrate how material from the protoplanetary disk accretes onto the star, contributing to its growth and mass increase. Protoplanetary disks also play a crucial role in planetary formation. Material gathering around a young star begins aggregating into larger bodies that may eventually become planets, moons, or other celestial objects. Studying the structure and composition of protoplanetary disks around star L1527 allows for an in-depth exploration of planet formation processes and an assessment of the likelihood of life emerging in space. The formation process of L1527, also known as Iris 04302+2247, represents a unique stage in the evolution of a young star. L1527 is actively accreting material from its surrounding protoplanetary disk. This process significantly influences the formation of planetary systems, as most of the material necessary for forming planets and satellites resides in the disk around the young star. Protoplanetary disks, like that of L1527, consist of gas and dust gathered around the stellar embryo. It's important to note that the formation process involves not only the star itself, but also its environment. A young star, such as L1527, emits intense radiation and particle streams that affect the surrounding disk. These processes not only contribute to the star's growth, but also influence the disk's evolution, its chemical composition, and structure. One key aspect of L1527's formation is material accretion, where disk material gradually gathers, forming solid particles and eventually planets. Accretion plays a crucial role in the evolution of protoplanetary disks and initiates the formation of planetary systems. Over time, more and more material accumulates around the star, forming protoplanets and other celestial bodies. Additionally, L1527's formation process involves the dynamics of its protoplanetary disk. Disks around young stars are not static. They rotate and can be influenced by magnetic fields and gravitational interactions with other objects in stellar clusters. These factors affect how material in the disk is distributed and accumulates around the star, forming bodies of various sizes and structures. The chemical composition of L1527 is also pivotal in its formation process. The disk comprises various elements, including volatile substances, heavy elements, and molecules essential for life formation. The chemical composition of the disk can significantly change over time due to stellar radiation and chemical reactions in the gas and dust phases. Understanding these conditions is crucial for comprehending the environments around young stars and how they influence the further formation of planets. Star 1527 is a unique object in space currently in the stage of formation known as the protostellar phase. This star is located in the Taurus Nebula, approximately 450 light-years away from Earth, As of today, star L1527 is actively gathering material into its protoplanetary disk. Within this disk, material gradually accumulates under the influence of gravity, forming rings and zones from which planets may eventually form. Over time, the protoplanetary disk of star L1527 will gradually dissipate. This occurs as disk material either aggregates to form planets and celestial bodies or disperses into space. This process typically spans millions of years, leaving behind a star with a formed structure, no longer possessing a protoplanetary disk. Star L1527 has the potential to evolve into a fully fledged star with its own planetary system. Studying such objects helps scientists better understand the processes of star formation and planetary formation in the universe. These studies not only expand our knowledge of space, but also provide insight into the possibility of life forming in other corners of the galaxy. The future of star L1527 is tied to its gradual development from a protostellar disk to a stable star with a probable planetary system. This process demonstrates the long and unique path that each star undergoes on its journey to its mature state in space. The scientific significance of observing young protostars like L1527 lies in their ability to help scientists understand the processes of star formation and stellar evolution more deeply. L1527 represents a protostar in its early stage of star formation, which makes it particularly intriguing for astronomical studies. One of the key objectives in studying young protostars is to understand the exact processes of star formation under cosmic conditions. L1527 is an excellent target for studying the initial stages of this process due to its youth and relatively high activity in infrared emission. A crucial tool for studying L1527 and similar protostars is the ALMA, Atacama Large Millimeter Submillimeter Array radio telescope, officially opened on March 13, 2013. It is capable of detecting and analyzing emission from molecular gas and dust in cold regions of space. ALMA enables scientists to obtain high-resolution images and spectra, opening new avenues for studying the structure and composition of protostars. Studying young protostars also plays a vital role in understanding stellar evolution. Observations of changes in brightness, chemical composition, and the surrounding environment around protostars allow scientists to infer the processes occurring in the early stages of star life and their impact on the surrounding space. One of the interesting features of L1527 is its disk-like structure surrounding the protostar. Studying the structure and evolution of such disks helps scientists better understand how planets and other cosmic objects form in our galaxy. Additionally, L1527 is a subject of intense research in astrochemistry. Astronomers analyze the spectra emitted by the protostar to determine the chemical composition of the surrounding gas and dust, which helps understand the presence of elements during early stages of star formation and their interactions. Studying the formation of stars and planetary systems plays a crucial role in modern astronomy and astrophysics. The data obtained can refine existing models and deepen our understanding of accretion processes and interactions between gas and dust clouds. This is critical for understanding the general principles of star system formation in various galactic conditions. Furthermore, data analysis allows us to expand our knowledge of planetary formation dynamics. Research indicates a variety of conditions under which planets and their massive satellites can form. This is important for understanding the origin and development of planetary systems in our galaxy and others. The data not only deepen our understanding of star and planet formation, but also underscore the importance of further research in this area. Continued observations and analysis of the evolution of star and planetary systems will contribute to expanding our knowledge and potentially discovering new key aspects of this fascinating part of our universe. Subscribe to our channel to stay updated on the latest news and discoveries in the fields of astronomy and astrophysics.